Hey guys, we'll be live any moment now. I'm just waiting for the Redwood City side to get their stuff together. All right. So you guys let me know when you're ready. Just flip the thing. Okay, we are live then.
Oh, this is a screening.
We need one over there too.
I was just about to talk about something, but I'm not gonna.
Oh.
I would just so.
And yeah, Matt, you can see it and everything.
So what is the proper
Yeah, I'm good.
pronunciation for that town in Italy?
Bologna.
Bologna.
Bologna, right.
Okay, let's-
Yeah.
yeah, so feel free to just take.
Yeah,
control.
so
You got it.
thank you very much. So essentially, this is the continuation of the introduction I made last Friday. I don't remember.
So we're continuously learning about you.
Yeah, exactly. So I guess this particular research meeting will be about the work that has been carried out at the University of Bologna and in the last few years without trying to summarize that and point towards a specific direction we are trying to.
I got it.
Yeah, it is okay like this. You can hear me well. Okay, that's great. Okay, so I guess we can start from the outline here. So we already discussed a bit of the vision behind this kind of work and the trajectory we are trying to address. So we're going to just move to the second point here, the brief state of the art of continual learning, in the context of machine learning. And I think that you already covered this in a previous research meeting with Lucas, I guess. So I'm going to go just fast on that, and then we can focus on our specific idea and proposal with respect to continual learning in the short term within the context of machine learning. And then I'm just gonna go through our current work, so what we're currently doing, so that we can maybe find some things on which we can focus on and work together to address this vision.
It would be correct to say that the work you've done so far is not been biologically inspired.
No.
That's something you're interested in.
Exactly. So from a very high level, we always try to move towards that direction, but it's nothing really compared to what you are doing here. So I mean, in terms of level of abstraction, and so it's pretty much aligned with the machine learning vision of inspiration, of biological inspiration. All right, so let's go. Okay, so I guess this was also for a more machine learning oriented audience, but the idea is that in continual learning, what we are trying to model is the stability plasticity dilemma, right? So this idea that it's a trade-off on things we want to remember that can be biased as well, and things we want to learn. So it's not just accumulating knowledge, it's somehow trying to come up with a generalized knowledge of the external world, which is always better and better as we move forward in our life, right? So it's not just an accumulation of concepts there. It's a much more complicated trade-off. And well, so this is also very well known for biological systems. But in what happens in deep learning, especially in gradient-based architectures, is that we are very much plastic in the sense that we tend to suddenly erase all the knowledge about the past we have encoded in our parameters, in our parameterized model, to suit just the new data distribution we encounter as we move forward, for example, in a stream of sensory data. And this is known in the literature as catastrophic forgetting.
I mean, it's funny because that term implies like a failure, but in deep learning, it's just the way the system works. So people erase things and start again, right?
Yeah, I mean,
so it's not like something that says catastrophically happens. It's something you do. Is that correct?
Yes, yeah. I mean, it happens suddenly, so that's why they label it a
Because I did
catastrophic.
it, right?
Yes, because
No, no,
I-
no, if you try to get a machine learning system to learn continuously, you won't be able to.
Yeah,
Don't
but-
forget, it's not like you want it.
I know, but they don't do that, right? I mean, they don't, I mean, my.
in general, you have
They
just
do forget.
I say people don't
You forgot for
put a machine learning model to learn several steps.
yeah.
That's what you mean.
But they want to.
Well, I'm just saying, it's not like the systems work continuously learning most of the time, and every once in a while, they, an event happens. Is that, I mean, my understanding, we're talking about here, deep learning, the convolutional neural networks basically can't do continuous learning, right?
Mhm.
So people just erase it and start again.
Yeah.
Right, or you would oversize your network in a way that that limit is so far out that you don't encounter it.
No, that's hard to do.
But they don't even do that.
Can't do that.
They can't keep adding. They basically have to train on the entire data set. My understanding is
Yep.
multiple times to get the whole thing to settle before you can do anything with it.
Mhm.
And if
Yeah,
you want
so
to add
that's why
anything
you
new,
can, that's so, in a continuous learning setup, that's the problem.
yeah. So it's funny because, all right, I mean, all right,
It's
No, it's
correct that that's the way, deployed systems are today. They're trained in a batch mode and then they're frozen and that's it. But that's not what we want.
I know, it's funny. I just would have thought, I'm familiar with the term catastrophic beginning for a long time ago.
Yeah.
And to me, we see the biggest problem in deep learning, I would say, is they don't learn continuously. Not that they fail, it's just they don't do it.
Yeah.
And this is the reason. I mean, this is the underlying reason.
That's why they can't learn continuously.
All right.
I would add to what you said, that actually system projection usually retrain the model. You have like a big initial training batch to retrain the model, at least every week. So there is also a continuous learning problem. It's not the problem of learning several tasks, but of learning a distribution that's constantly like shifting
Mhm.
here and there.
Yeah, we'll be discussing about that also. So, and then I have an example. So I hope
Okay.
we clarify the forgetting part.
I use it for it. I mean, this implies that the deep learning systems are working and every once in a while they have some catastrophic problem. That's not really true. We just don't deploy them this way.
I think this is under the context of continuous learning. This is not the biggest problem in deep learning. period. It's
Yeah,
the biggest problem in deep learning for continuous learning.
yeah, yeah, exactly. Maybe that's better. Yeah, so I have an example. I have an example here that I think it's clear enough. So let's say that we are in the context of a system for object recognition, right? So we have a number of incremental batches we encounter over time, and each batch contains images belonging to 5 different classes of objects we have never seen before. All right. So essentially, what you would expect from a system is if we test, and you can see on the left the graph where we have on the y-axis the accuracy of the whole system tested on the whole, let's say, possible objects that you will encounter also in the future that you have not encountered yet. And then on the x-axis, you have the number of training batches that was explained before. Then you would expect a system that can grow over time in terms of performances, right? But what you can see there on the left is essentially a flat line in terms of accuracy. As what happens is that the system, as soon as encounter a new batch of data and tries to distinguish somehow the images belonging to this batch of data, and it suddenly erase the knowledge about the previous encounter classes objects. And you can see that also from the confusion matrix, the evolving confusion matrix on the right, where these vertical bands essentially indicate that the network is only guessing among the newest classes it has encountered, it has learned from.
And the old ones are kind of fading out.
Yeah, exactly. So this is catastrophic forgetting in your network when you just continue backpropagation on the new training batch you are facing at a specific time so I guess this is
It's pretty dramatic.
okay. Yeah, it is pretty dramatic as you move to now.
Although, I mean, like, I'm used to like even more dramatic forms of catastrophic forgetting, though, right? Like basic Hopfield networks, right? The most basic of all networks, right? It's not just that you can't learn new things and the old ones cannot drop out, so it gets worse. But it's actually that at some point the whole network turns to shit and it doesn't do anything anymore.
Mm-hmm.
So it's that's why, like, how I register the term catastrophic,
Yeah.
right? And not just really bad, but catastrophic.
I mean,
just
this is kind of
crashes.
catastrophic. The performance. I mean, in this kind of setting, I think that you can reach in a training on the wall training set, you can reach 85% or something accuracy.
Right.
So I think at the end of the training, just 10% is really not working.
So let me just to be clear, this is not a capacity issue. Like
No.
if you were to train
Exactly.
that network on the entire system in a batch mode, it would be fun.
Exactly. You
Right,
can
it's
reach
just-
85 or more % of accuracy.
Yeah, yeah.
All right.
It's just the
Yeah.
fact that you're not training, keep training. You don't.
Yeah, it
keep
would be nice to
training
show that
yourself.
in parallel, then you would
Yeah.
see the difference, right?
Yeah, so essentially what we do in our
Yeah, that would be
experiments
good.
is to compare our continual learning algorithm with a cumulative, let's say, training strategy. That is, every step in time, we accumulate all the data we have encountered so far, and we retrain the whole system from scratch. That's incredibly wasteful, but it's our, let's say, upper bound.
Yeah.
And every time, it's not a capacity issue, you can see from that particular curve, right? Because you can tell the difference between the continual learning curve and the cumulative one.
Is this like a common data set? No.
Oh, this is from Core 50, yeah. So the data set we proposed, and we will talk later about that. So I don't want to go into details here, but the idea we proposed also in this preprint that you maybe discussed, continual learning for robotics, was to divide in a fuzzy categorization these strategies in 4 different categories. So regularization approaches, rehearsal approaches, generative replay, and architectural approaches. So the idea,
I'm sorry, these are like 4 different quadrants.
4 different, I would say, categories of continual learning approaches that we can.
You're showing them so there's 4 different dimensions, but you're laying them on a 2-dimensional picture. Is that right?
Is each of these levels at one of these?
Well, it's a Venn diagram, right?
Yeah, it's
So
But
you're using the different zones to still be able to represent 4-dimensional
Okay, so
structure.
This is the only way to have all the possible combinations. Yeah, this is particular. I mean, I don't know if there exists.
I guess am I supposed to read this as like regularizations on the left and architecturals on the right?
No.
Oh.
Each color
Exactly.
is one of these categories.
Oh,
So it's a
I
Venn,
see.
it's a Venn diagram.
So the yellow is regularization, architectural is
Exactly,
blue,
exactly.
rehearsal is green, I got
Yep.
it.
Yeah, I think if you put a little arrow there, it would have been.
Yeah, maybe it's better, or the
And also
respective
The
color.
fact that they're like ellipses makes it implies there's some dimensionality to it.
Mm.
But-
No, it was just the only way you can have all the possible combinations.
Yeah.
See all 15 combinations.
Yeah, I mean, it's kind of tricky. The first time I draw it, it was a bit.
So basically you're saying there's some overlap between some of them between 2 of the approaches, but nothing's in 3 or 4.
That could be, but at the moment there's still a
Yeah.
few approaches that can.
Could you just quickly explain sort of the big?
Yeah, exactly,
I
that-
know what
yeah,
regularization
exactly.
is, but what is meant by generative replay, right?
Yeah, so the idea is that that was the idea to explain just the general approaches. So the regularization category involves all the strategies that just regularize learning over time. So the idea is generally to add, for example, a regularization term to, for example, change as little as possible the weights that are important for the previous data distributions.
Does that include like, here's a data set, make sure I intermix all the different categories and train multiple times? Is that what that is?
No.
I don't think so. And it's just, for example, for L1, L2 regularization that are used in machine learning to improve generalization capabilities or drop out, or something we discussed previously. So all possible strategy that can somehow regularize learning, right, over time.
So regularization, I mean, there's a goal that it's trying to
Yep.
achieve.
Yep.
And it can be multiple goals. You
Yep.
just mentioned one of them, which was to try to leave the weights as small as possible, but it's.
Yep. Yeah, in this case, it's more as maintain as stable as possible the weights that are important for the previous data distributions in
Right,
account.
but I guess it needs to be kind of spelled out because there's so many, I mean, it's a strategy to get all sorts of different things.
Yeah,
Well,
we'll.
it's well known in the machine learning field that
Right.
you know, that's
understand
adding some terms to the cost function.
Yeah.
Right, as a technique, yes, but as the goal is what I'm trying.
Okay.
Yeah, we discuss maybe something within the strategy we proposed. It has also a part of regularization
Okay.
part AR1 that down there.
This is all within the rubric of,
Yeah.
these are ways of achieving
achieve to work within the gradient-based algorithms, but still trying to address the problem of learning continuously. And so the second category is the Inertial approach, in which we are allowed essentially to have a fixed size external memory in which we can put great examples of the past, representative examples of previous distributions.
So that may be similar to what you were saying, like have some previous stuff that you keep showing.
That strategy is working very well in practice. And then we have the
But you
general.
told me that recently, I mean, the way these things are trained, they go through the data set over and over and over again. Is that right? I mean,
Some percentage of it is.
A very little percent.
not all of it.
Not all of it.
Also, the idea of rehearsal is to do part of that, not the whole batch of everything,
Yeah,
but
no, exactly.
but you want to
Very
find
small
a couple of
percentage,
good representatives.
Yeah.
In general, a very small percentage, like 2-3%, it's already okay to somehow reach the cumulative core.
Is it important that 2 or 3% is chosen wisely, or could you do randomly choose in the past?
You can also randomly choose, and for our experiences, it's okay to do that, but we haven't explored that particular factor.
I mean, it'd be kind of hard to know what ones you should check, but
Yeah.
you should select for the.
There are various metrics you can use in the embedded space, in the input space. So you can say, hey, I want them to be as different as possible to cover all the space. All possible ideas. Okay, then we have the generative replay approach, which is more used nowadays with the adversarial networks that are now more and more effective in producing images or projecting again in the input space, high-dimensional input space, the data we have seen before. So the idea is to compress somehow the information about this data in a external model, machine learning parameterized model, and then generate back the images we are going to use to rearch. So this is the kind of approach.
Won't that system also have catastrophic forgetting?
Yeah, exactly. So that's but in general, the idea is that you can compress a lot of information, so you can store it. There are various techniques to somehow don't be affected by continual learning on that part, and work maybe on a lower dimension that is more stable, and then to project back the images.
Just so I understand this right, it's a form of auto-generative replay, right? I mean, the
Yeah,
model that you learn, you use to generate something,
Exactly.
and you reason that the stuff that you are generating has a lot of good information.
Yeah.
So you want to learn that again.
Yeah, I mean, I'm not a huge fan of this approach.
Is getting around having more labeled data, is that the idea?
Well, it's still on the idea you want to have, since the input space, you want to have also information data of the previous data distribution you don't have anymore into your in your training batch.
Would it be a subset of the rehearsal?
Yeah, it can be a subset. Yeah.
So you're kind of
essentially
dreaming up examples.
Yeah,
So I'm trying to
exactly.
understand, is that better than having new samples, or is it just a way of getting around the fact that you don't have to have many samples? I mean, like when DeepMinds did their AlphaGo thing.
Yeah.
They ended up having the machine play itself over and over and over, because that's quicker than having real games.
Right.
So it's not that those games are better, it just means that it can generate lots of games. And so the question here is it just a way of getting around having lots of labeled data, just make new data, or is it really somehow better?
No, I mean, in this case, you want to somehow maintain a kind of a memory of things that you cannot generate anymore and are from the past, right? So if you have new objects you want to recognize, you learn from them, but you have to somehow, at least at this moment, being able to generate back all the objects you have seen before, otherwise you will forget them.
Or you could just rehearse them again.
Yeah, as if you have an external memory in which you store
Okay.
image. But in that case, you don't have this external memory, and you want to generate it back somehow. And someone is pushing on that direction with the idea of having less memory overhead, I guess, in that particular case.
But when you generate them, you still retrain on the generator.
Yeah, exactly. You mix them with the real images from the current training training batch, and then you.
I guess to Jeff's question, is this better than rehearsal? Suppose you.
I don't think so. I don't think
images, but you could have stored 100 images.
No. It's I don't think it. I mean, for my knowledge, it should be. It's not better actually. It's worse.
But you can generate images that have never seen before. So in that sense.
Well, that's the question. Could it be better?
But you're not going to generate images you've never seen before that somehow have information you've never seen before. I mean, it's not gonna make up, like, oh, well, now I know what a cat looks like from the rear. I mean, it's just not gonna do that, right? So,
It has some sort of a generalization, so it works like a very good data augmentation.
yeah, but they can't literally create new knowledge that they didn't
No.
expose before. That's
So
impossible.
I guess this is the question. Suppose you could rehearse 1,000 images, or you could generate 1,000 images, which would be better? You're saying maybe the generated could be better
Right.
because it
We
can.
augment data as well, right? So when you train a classifier, you're gonna blur the image, so it generalizes to images which are blurred. We can test that. And
Yeah,
the idea behind a generative, you could do the same as well.
if it's really a
So that
powerful
was my
generator.
question, Which is it that, or is it just?
No, I mean, that
You're
maybe is,
saying you don't think it's really better. You think
Yeah,
it's just a memory
yeah.
thing.
for now at least it's
Yeah.
like that. So then we see if, especially if you have a bit of creativeness and something else, of course, if you can generate something you can learn from, right? Also, our reasoning system does that, I guess. If you can generate new knowledge from the existing knowledge, but we'll see about
I
that.
mean, that's always fascinating. Just to give a weird example from humans, right? That you can learn from imagining shooting hoops, and you actually improve. Almost as good as people who do actual shots. But you have to tell people to really like super vividly imagine it. So the physics engine that knows how a ball behaves can like that actually even works in theory, which is super surprising. But the results are real.
It's better. I mean, like, athletes do that, right? A
Right.
skier will sit there and then mentally rehearse the whole run,
Right.
and they can do that over and over and over again. I'm not sure that that's actually better than doing the equivalent number of runs.
No, but it's cheaper.
It's cheaper.
It's
It's
cheaper,
It's like instead of having to do the whole thing, I
Yeah.
can do it quicker. I can just, 5 in the evening, and,
Right.
so I can see that.
I guess the best you can.
But that's really an efficiency point of argument.
Yeah.
That's more like I don't have to do it.
Exactly.
I guess the best thing is you can't create like a novel skill. What you could do is you could rehearse. If someone is presented.
Yeah, that was my point earlier, Tony. You can't make up new knowledge, right?
Right.
You can't just come up, I can't imagine part of the ski course if I haven't skied it.
But in the sense that if you've observed it once, but haven't experienced it directly, you can maybe make a mapping to things, in your experience that were similar to that enough to try to link those together and kind of bring them up to current memory, if you wish, type of thing. So in the generative replay, what you're doing is you're making something more robust under certain prior assumptions that, we will add some noise, we'll add some distortions, we add the known things to distort the thing. But for instance, if you hit something novel like, what does it look like through fog? It might not be able to handle that because you built in the degrees of latitude.
So I can imagine it could have gone both ways. And so my question to Vincenzo was really just an empirical question. What have they found? Did they do this because it makes it better? Or they do it because it saves them, and what does the empirical results say?
I think for now we're still on the early days of generative play approaches. We're still working on I don't know, MNIST images, and with respect to maybe other approaches that can scale much better. It's still
Maybe we don't know.
we don't know yet.
Right now,
We don't know yet.
yeah.
But that
Rehearsal is the best so far.
for now.
Okay, all right. So-
Exactly, and then the last part, maybe it's also somehow related to the HTM cortical learning algorithm implementation. Is more about approaches that can change the architecture of the system. So new weights, new connections, maybe freezing some part of the network and
Clearly,
reducing.
in our world, the obvious thing here is active dendrites and compartmentalized neurons, right? Compartmentalized neurons allow you to do compartmentalized learning.
Yeah.
And compartmentalized forgetting. So, yeah, I understand.
So would it be fair to call architecture also just plastic?
No, I think everything's plastic, right? It's more of a, in our case, I don't want to tell Vincenzo what he's going to say, but for our case, the power of the networks to learn continuously is that you can form, a neuron can learn something new and hundreds of new things and not affect the other stuff it's learned.
Right.
And it's
That's,
because you physically compartmentalize the
Yeah.
synapses into different
Yeah.
segments.
That's true. Yeah. Right.
So I learn on a new segment.
Right.
And the old segments are still there and the neuron doesn't care. doesn't get confused.
Yeah, I'm excited to look more into these
I mean,
because
that's
it's,
like a fundamental, I think that is one of the most fundamental ways that brains do continuous learning.
Yeah.
Not the only thing, but
And you have to have sparsity to do that.
you have to slice it, and you have to have compartmentalized neurons.
So is there some notion in these various techniques that there is an implicit policy as to what's worth paying on to? Some of these things are basic empirical. If I see it, I'll hold on to it and then it decays away. But for something that actually, like, retain a memory that you might have access for years and years and
Yeah.
years, but it's still there and somehow it's important. So in all these techniques, is there implicitly a policy on what is important?
yeah, I guess the implicit policy is that everything is important, that you want to preserve everything.
That's not true in our
Yeah.
work. Our work is not true like
Yeah.
that at all.
Right.
Our work is these synapses have a permanence. and
Yeah.
Permanence is really reflective of how many, there's some formula which you're going to use to apply to that. It could be as simple as how many times have you experienced.
Yeah,
But
exactly.
it's probably going to be a time-based thing, how many times you've experienced, and it's also going to be in the brain will be influenced by certain neuromodulators. So you can have an emotionally salient thing that's going to be remembered instantly, and it's never going to be forgotten.
Yeah.
The point is, each synapse has this idea of how much it should be kept around. And it's a separate calculation from its value in the network.
That would be interesting, actually, to augment these benchmarks with explicit things that maybe you don't need to remember, or
Yeah.
it's not important or something.
But when you mentioned, something emotionally salient, I mean, something emotional tends to lock something, and it's tagged at that point,
Yeah.
whether it's stored in a different place or whether.
No, you can just store it the same way, you just make the synapses so they don't go away.
Right.
It's like the synapse, this one's gonna last a long time, and the other ones are gonna go away because they don't.
Do we know how emotions do that?
We do to some extent.
We have neuromodulators.
Yeah, neuromodulators are released throughout the different areas diffusely throughout the cortex, and they change the way these synapses learn. And so they can, you can learn a new synapse very quickly, but you can learn new synapse very quickly and say, this one's gonna stick around for a long time. And I don't know the literature on that. Maybe something else does, but that has been studied, and there's, there are chemical and genetic changes that occur in a cell to make some synapses really permanent.
So for example, it's known that like dopaminergic projections, so dopamine gets released, right, whenever there's surprise. So it's not a reward molecule, it's a bit of a misstatement, because even if there's no reward, you might get a dopamine signal if you thought you would get a reward. But the point is you've seen in cell cultures that tiny bit of dopamine can actually make the exact same synapse a lot more plastic. So stimulation protocols that did not induce long-term potentiation, suddenly, when there's tiniest amount of dopamine present, those same protocols do induce a sizable amount of plastic change in the synapse. And so the argument is that the brain has ways of transiently up and down regulating very targetedly, because they're trisynaptic circuits, so you have pre-synapse and the post-synapse, and then there's a third synapse that releases the dopamine very targetedly. So you're capable of building circuits that will temporarily boost plasticity. So it's a metaplasticity.
I didn't know that. So the dopaminergic synapses are spine specific. I thought it was a more general release.
Both exist. They're tonic and well, actually it's three-dimensional, right? Because so there is these global releases where like whole areas get like inundated with dopamine.
Yeah.
There are trisynapses where it's super specific.
I know there's some of those, but I didn't think they were very common.
No, specific brain areas that have a lot of those.
Okay, but if I look at cortex in general,
Yeah.
if I see like dopamine.
The prefrontal cortex has a lot of dopaminergic, like subcircuits.
But specific, you're saying?
Yeah,
I
specific.
thought mostly in the cortex it was more diffuse release.
Yeah, I'm not exactly an expert on that, on like sort of overall cortex. I just know that they are quite particular, like in hippocampus and entorhinal cortex and in prefrontal cortex. You find a lot of those.
Yeah.
And then there's of course also the specificity in time. So there's these circuits that are like have a tonic release, and then there's the ones that are very precise in the time, particular projections from the basal ganglia. So the action selection mechanisms and things like that, reward learning, where you get very targetedly, like over a course of 200 milliseconds, here's a window for increased plasticity, and then it's over.
So it gels after that. you're saying. So in other words, the plasticity you're talking about says things can jumble somewhat, and then after this period, they freeze.
They're frozen again,
They-
exactly.
Okay, so that's the key thing, because
Right.
you kept saying, dopamine makes it more plastic, and it's saying, well, then you're more subject to losing stuff.
Yeah, that also would.
You could have two synapses that have the same efficacy in the network, and one of them is gonna be like, etched in stone, and the other ones could go away.
Right.
There's a physical change to the synapse that makes some just more permanent.
Right.
Ossified.
And of course, the big mystery is, right, how does the brain, decide and know where and when to, project dopamine? Because, these are neurons. They're just different in that they don't transmit a spike, they transmit dopamine. So they don't depolarize, or hyperpolarize.
So I think one of the theories is, it's sort of like, if you've gone through a series of things recently, and a whole bunch of synapses have been activated during this recent transition, that there's a bit of a memory in those synapses about that they were active recently, and then you inject something like dopamine, and all the ones that got activated recently can, okay, well, all strength can become more permanent. This is what do you call it?
Right. It's the argument of a synaptic trace. So
Yeah.
it doesn't need to be at the moment. It can be a little bit after, and the chemicals cascade will still, be working.
So one of the lessons we've had about brain stuff is that the synapses are very complex systems that go well beyond just its efficacy or its weight. And they have another life, which is very much related to this issue of continual learning about, how are they permanent, when are they formed, how easily are they forgotten, and so on. And so that's just like none of this stuff exists in today's neural networks. And I think that's all in the architectural realm there.
The way you guys
Okay.
like the video if you're
So maybe
enjoying
I
this,
can go
please.
faster on this.
Yeah.
Yeah. No,
You're
problem.
provoking a lot of discussion.
Yeah, that's
here.
great. That's great. So if you also want to talk one-on-one and all this stuff, we can also discuss it later. But essentially, I wanted to cover at least some of the works and ideas that we want to push forward. So I won't go into the details, of the framework formulation we propose, but essentially, you can expect a learning algorithm to encounter a stream of data that can be one example at a time, can be multiple examples in a specific batch over time, but you have to essentially update the model with only those examples, and eventually you get also a contextual information, an external supervised signal that tells you we are solving this particular task, we are in this particular room, voice command or whatever. So with the idea of moving towards a common framework that can be used also in robotics, that was the idea. And then to evaluate all the possible continual learning strategies as well. So what we would like to...
What is H?
H is the model, essentially, the hypothesis at the time step.
That's the state.
Yeah, it's the state, essentially. Then B is the batch of data. M is the external memory. Eventually, you can use that. People use that, so we integrate it into the framework as well as a separate thing with respect to the state, the hypothesis. And then the eventual T of I is the task supervised signal. And the algorithm should update the hypothesis and eventually the external memory.
And these the test.
And these are, essentially data distribution that you encounter from which you draw the examples of P of I. But yeah, I don't want to go into details here. It just it's not interesting now. But the idea is that since many strategies here that have been proposed in the last 3 or 4 years, they are pretty much, many of them are concerned with the idea of learning over multiple tasks. So the idea that you have a particular object recognition tasks with several objects, and you move to another vision tasks or different objects or very different distribution. But with the idea that you have a very big training batch, training set essentially of the entire task.
Of continuous learning.
Yeah.
It's not really just.
Yeah, exactly.
It's more of a multitask.
Yeah, exactly. Multitask, but in a sequential way. So that's a novelty, that you don't have access to the same task or task data at the same time. And that is something that we are not really interested in. Of course, you can have an external supervised signal contextualized signal that tells you we are in this room, we are solving a different task. That can help, and we should use that when we have it. But the idea is move towards rehearsal-free and task-agnostic online continual learning. That's at least for us. So the idea that you don't want to have an external memory, you want to store things into the activations, the weights of your network, in your parameters. And then you don't want to use the T signal. So you have just one task. Essentially, for example, an agent should be able to act in the world with a fixed set of outputs. I would say sensory outputs, whatever it is. But the idea is that it should be very we should be agnostic with respect to the specific task, and eventually use that for specify the behavior of the agent. So just something that you can add on top, but essentially you should be able to learn continuously without that particular signal. And then the idea that we want systems that can work within a bounded computational memory overhead. So now we see many strategies, they still have this idea that it is allowed somehow to grow very little, probably linearly with respect to the tasks or batches that you encounter. So that's something that we don't like.
Related to rehearsal free. I mean, in some sense, rehearsal free says I can't store data, I can't reuse it. Online, where it implies that you're doing it in real time, is the only difference here you're saying online is bounded in terms of its memory?
Bounded.
And where rehearsal free could be a system that keeps growing? Is that the only difference?
No, rehearsal free is the idea that you don't want to store the data that you encountered before, right?
And online says that too, right?
I mean, well,
I guess I'm trying to understand the difference between rehearsal.
Yeah, I mean, I don't know. It can be also an online. That could be also an online strategy that can use some kind of rehearsal, right? Keeping some images into the memory and probably not. I don't know.
I don't know. As soon as you say real time,
yeah.
I'm assuming you're not taking any time to go off and rehearse.
Yeah, it depends. The idea of, I mean, it's not really, especially online. In this case, I assume it was more on the same word that you used in your paper as well. So the idea that you have one example at a time, right? So in a streaming input, streaming data, you just want to process one example at a time. And that should be rehearsal free. But maybe you can have a strategy in which you process one example at a time, but you use you train, you update the model using also other images. But
okay.
It depends on how you want to see that, but online.
Give a software program one more data, it can learn, but internally.
Exactly. So it depends how.
This is saying don't cheat. You can't.
Exactly.
Really rehearsal.
So think of playing memory, and you're forbidding people from rehearsing in between moves.
Yeah, right. But that seems like subtle difference.
Yeah.
Why the focus on rehearsal? We humans do some rehearsal.
Yeah. What I think is that what I like to work towards is the idea that you can do rehearsal somehow in sense of generative replay, but you don't want to store high-dimensional raw data. I don't think we do that as humans. We have some kind of.
I mean, it's human. I can practice something once. I can practice it 2 times, 3 times. All of it works, right? I don't have to practice it 100 times before I get any benefit out of it. So to me, it's just sure I can do things over and over again. But rehearsal is not required to learn something. I can learn something new with a single experience. I may not learn it as well as if I spend a lot of time playing with something.
Yeah.
So I view it as sort of brains aren't required to rehearse.
Yeah.
They get better when you rehearse, but they're not required.
Right?
Oh, with the idea of the complementary learning system, maybe there's some kind of
Yeah. So I mean, the argument is if you stop the brain from rehearsing, right? So there's these fascinating interventions that some people have done with respect to hippocampal replay during sleep. When you prevent that, you will not be able to form long-term memories, right? So after 2 weeks, whatever you learn.
Okay, now we're talking about the issues of memory, long-term memory formation in the hippocampus.
Right.
And other things. So
Right.
I wasn't getting there in general.
Yeah, we meant one-shot learning in terms of like, right, in the moment.
There's other things that are complex in the brain that I'm not talking about. The general rule is that,
Yeah, the general rule is we stream learn, right?
Yeah.
Right.
So before you go,
Yep.
just to understand, so rehearsal free doesn't necessarily mean that, for instance, I take the information in, I process it to the first 10 layers, so you have a very compact representation of that thing. I can hold on to that as a side thing. It's just you don't want to run through the first few layers of time, or do you say, no, really, there's no encoding of raw data whatsoever? I just want to know where you're drawing the line.
No, the line is on raw data input in the input space.
Okay, so you could have an encoded version, very compact form of this, and one would argue
Yep.
that.
Internal
Yeah,
rehearsal.
exactly.
Or whatever. So it could be having a trace of that information.
Yep.
So it
Yeah,
is-
yeah.
Okay, all right.
Yeah, I think that's possible. Still, what I want to avoid is to store high-dimensional data, right? Images, right? It's not really interesting to me. So we are in this context where you have a number of incremental batches, and in these batches we can have different things, right? So we can have new instances of the same classes. We are in a classification, let's say task, new instances, new examples of the same classes, or completely new classes, or both of them. So this was just the setting which we are working on, and without this kind of supervised signal with respect to the task or a task boundaries is called sometimes. Then we are using the Core 50 dataset, which I'm not going to talk about, but essentially something we proposed in 2017 to work directly on continual learning for object recognition. So it was one of the first benchmarks and dataset proposed with this respect. So this is very important. It's a video benchmark. Essentially, we essentially capture a number of I guess 11 different sessions for 50 different domestic objects with Kinect 2. So we also that information, other things. So you can do essentially recognition, detection, segmentation in a continual learning fashion, let's say. So essentially,
He's getting really confused because these pictures of all these old phones and no one's going to know what they are.
Exactly. But it is that you can still learn continuously, so that wouldn't be a problem. So
Is that a problem?
What's that? I don't know what that thing is.
There's this weird ball that's not round.
Yeah.
It's like oval.
Yeah.
What is that?
It's for the.
I know. Europe, you don't see that.
So that the idea in this last work is called fine-grained continual learning is to move towards a much finer grain of training batches. So the idea of moving towards online continual learning, since we started working with kind of training batches of 300 images, and then we are now able to work efficiently with 391 training batches with just 300 images of one class. That means that we can really start working at the edge for continual learning systems, because, for example, for Core 50, we had images were captured at 15 frames per second. So the idea is now that 300 images of one object, it's now I guess how much is that? 20 seconds to that is kind of okay for a learning system. You know, if you have it on a single camera to work really in a, let's say, towards an online fashion and a responsive way. So in the graph below, you can just see that we, for the 79 version protocol of the benchmark, essentially we changed the object presentation disposition, and this vertical so the graph is like that, like this. You can see colored boxes that represent when the particular object is contained in a particular training batch. So it's how so on the x-axis you can see the training batches, and on the y-axis the 50 different objects. And well, the vertical gray bands here indicate that the first time that you see an object, right? A particular. So you can see that from the first version of the protocol, we moved to the more challenging, let's say, version in which you always encounter over time different objects, and the sparsity is a bit more since you see things in a more compressed way. You encounter an object, and you don't encounter again for a while.
If you see the same object again, do you see the same images?
No, 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 always different in different,
Always
in
different
different sessions,
images, right?
different backgrounds, different illumination, different outdoor, indoor.
Generalized.
Yeah.
It's like we saw in this so very different.
So you're not repeating.
No, exactly, never.
Okay.
And the idea is a system that can learn over time if it encounters new objects, new situations, new things.
Must be pretty challenging for.
Yeah, for continual learning system, yeah, it is, especially when you have a very non-ID
Yeah.
distribution, right? Because you have just one object, and all the images are very highly correlated. You don't have a very representative training batch of all the possibilities. Okay, so I don't know how much time I have left, but well, we can just start talking about our solution. Essentially, you can see here MobileNet V1 architecture is kind of a very good trade-off, at least for our perception, with respect to efficiency and also performance in terms.
MobileNet V1.
Sorry?
I don't understand what is mobile.
Yeah, it's just a particular kind of architecture that was proposed.
There's a second version.
There's a second version of that, so it was
Oh, that's
proposed.
not like V1 and-
No.
There's a MobileNet feature. There's different layers.
It's a slimmed down.
Not that V1.
Run on mobile systems, basically.
Yeah, so it's a very good trade-off in general. We think in terms of accuracy, performances, and
Right.
and efficiency. And so we stick to that essentially because we want to port then this solution to embedded applications and robotics.
Right.
So the idea here is that we treat this network as in a three-level fashion. So the lower part is essentially we start from a pre-trained network on ImageNet, but you can also think of learning essentially low-level generic low-level features. You can learn them in an unsupervised way or another way. I don't know. You can slowly fine-tune them. You can essentially they are pretty much all the same for all computer vision tasks. That's why we wanted to define here a threshold in which below this threshold it's not really useful for natural images to tune that representation with respect to the specific tasks or classes you want to distinguish. Then we have the upper part, we have class-specific discriminative features. We found it has a very good impact on it if you tune them with just with respect to a single linear layer on top. It can impact on core 50 up to 20% or 50% accuracy. It's important to have a few hundred or thousand, in this case, parameters to tune in that particular level of the network. And then you have the outer layer that you can also treat different, so the linear classification layer on top. So the second part, in this case, we use a regularization. They say in Air 1 star, we use a regularization technique to help somehow maintain the weights that are important for the previous data distributions, as we told before. And this is pretty much in line with a few modifications of the proposal from Ganguly here at Stanford that proposed a synaptic intelligence approach in which you exploit somehow the information of the contribution of each weight to the decrease in the loss over time. That's essentially what the loss is about there. To somehow estimate the importance of a particular weight for a trained model. And then you try to change as little as possible these weights that are important while learning on a new task, new batch. And essentially you have the loss function there. I don't want to go into details, but essentially you can add to the standard cross-entry loss function a regularization term that says essentially if omega k is a particular importance for the weight k, you want to say that essentially if you move away from the optimal weight theta k bar,
you're punished with some
Exactly.
square distance.
Exactly. So the loss is going. If you move that way, that is important. This loss is going to grow, right? So you want to disincentivate that, and so this works effectively. But in the original proposal, it was a bit hard to do efficiently because you have to maintain for each batch. We have 400 of them. Essentially an optimal weight and an importance weight. So it's kind of doubling sorry, 2 times more in terms of memory, and then you have also the computation. You have these are every time you move on, you have to add the regularization term.
It's only two things: the weight and the importance. The metaplasticity.
Yeah. And yeah, so it was a bit not. I mean, it was working well, interesting proposal, but then it had these particular inefficiencies, and then we tried to solve them in a couple of papers. But essentially, we came up with a solution that is working very well on Core 50 and other data sets, in which you just have one, let's say, importance weight, importance factor for each weight. So you can somehow summarize the importance of a weight over time with just maintaining one of those, and then we don't maintain anymore the optimal weight as well. So we have a formulation. Essentially, we change somehow the proposal so that we are tuning essentially the learning rate of each weight differently with respect to the importance of the weight. And so in this way, we can just have just one real value for each weight somehow.
Learning rate per weight.
Exactly. So essentially, you are maintaining a real value for each weight. That's the only overhead that you have. So in terms of to model plasticity somehow, we just tune the learning rate with respect to each specific weight.
Right, understand that is metaplasticity, but why does that not mean that? Like, how does that allow you to reduce the overhead? I don't follow.
Well, before
So,
there was
like-
two things per weight, I guess.
Yeah, essentially.
Well, how do you know now which?
It's not the
weights are
same thing.
important and
It's
which ones
not-
are not?
No, you still have to somehow compute the importance of each weight, but you every time you move along the training, phase.
Right.
But essentially, you can store just one of these. You can somehow summarize the importance of within just one real value. And I mean, I can point you to the specific
Right.
matrices.
Oh,
but,
you're saying before it was more than one real value?
yeah, you had to every time you moved from one training batch to another. You can essentially, if you want to respect this specific formulation,
Right.
you have to add an additional regularization term every time you move to another batch, right? So in this, for maintaining a new regularization term here, you need a theta k bar. That is the optimal weight computed on the previous task.
Right.
And then you have the optimal weight WK VU down there that essentially is incorporated with a few different hyperparameters in the bigger omega term there, K nu.
That's too fast for me to follow.
Well, but essentially you want just a real value encoding the importance of that weight for the particular task or training batch,
Right.
and then the optimal weight that you just came up after training on that particular task or batch.
Right, I understand. But so that still means you're keeping track of two numbers.
Yeah.
One is the actual weight, and one is the importance of the weight.
Yeah. That's the proposal.
Right.
No, that's the proposal. Then we don't maintain these two elements anymore. We just
So not two terms. I don't understand.
No, there are two terms always in my proposal, in their proposal, but essentially in this proposal you have to maintain these two terms for each task. In my case, it's just for the whole training phase, right? So essentially you don't grow linearly with respect to the tasks you encounter or batches you encounter.
Oh, I see.
What would be the advantage of having different, I think of them as permanence values or
Yep.
metaplasticity values for every batch?
Well,
Why
essentially
would you want to hold on to them?
you are specifying that for that particular chunk of data, you want to preserve these weights that match, right? So you don't have
Yeah, but why would that be important for the future? I mean, why
it
would
depends on the
anyone
data
want to
that you
hold on to
encounter.
them?
because you don't want to forget.
Well, but I have the weight. That is my not forgetting. That is my network that I'm training, right?
The way I've seen it explained to me visually is that, suppose you've learned a bunch of stuff.
Right.
Okay, now you have a new thing that you want to learn,
Mhm.
right? And you don't want to forget the old stuff.
Right.
So you want to make a change to this weight.
Right.
If you, there are a bunch of ways you can make changes to the weights.
Right.
So
achieve
that
the
you,
outcome. Yeah.
so that you learn the new thing.
Right.
A subset of those changes will not forget the old stuff.
Right.
But most of those changes will actually forget the old
Right,
stuff.
and that is
So you want to go in the direction where you learn the new thing, but minimally forget the old stuff.
Right. I understand.
So
But
so in order to do that, you have to maintain information about the old stuff in this way.
that I understand. But that is just the one value in addition to the weight. I don't understand what would be the value of keeping those metaplasticity values for all the different batches that you encountered in the past. I still don't understand why people were that wasteful before.
Well, machine learning is a very brute force. Because
I mean, it worked well. There are a few.
Like, how would you even
papers
use that? Because you're never going to encounter the same batch again, right? That's the point of continuous learning.
Oh, no, you are.
But you are testing on the old batches always.
Okay,
You
but
wanna
then
maintain that
if you do
performance.
that, how would knowing what weights you wanted to preserve back in that old days when you were training that first time, how would that help you?
You would constrain the possible weight updates you do to be consistent with the old stuff you've seen.
But you now have learned other stuff in between, so
It's a constraint satisfaction thing.
Hmm.
It gets harder and harder
Yeah.
as you learn more things.
Yeah, exactly.
To stay consistent with the old stuff, but without, at least in this way, without remembering what you did with the old
Yeah.
stuff. That's fine.
Well, maybe we can just keep through the results and then we can
Yeah.
discuss these later. But maybe they are more fun. But yeah, essentially we treat the last classification layer differently with this strategy. It's called CWR star. Essentially, we try to resolve somehow the stability plasticity dilemma with just having two different memories, one that is very plastic and one that is for consolidation purposes. And so we can in this way somehow work very well also in the context of different classes encountered over time, or something that is kind of very difficult to work and to address in continual learning for catastrophic forget. Well, so I don't want to go through these, but essentially these are the results in the incrementally difficult protocol that we have. So from 79 pages to 391 patches, and you can see a different, a few state-of-the-art continual learning strategies that are rehearsal-free. So none of those use somehow patterns that you store from the past. And so
What is CWR?
essentially the CWR strategy is just the way we treat the linear classification layer on top. So you can see that the green curve here is saying that if you start from a pre-trained network and you freeze all the layers below, you just tune the output layer, you can reach that kind of level of performance on this particular task. And well, under the graph, you can see also the percentage of average percentage of improvements in terms of memory and compute power with respect to the cumulative approach we have discussed before. So essentially, talking about the last protocol, the 391 patches protocol, you can spare on average 45% of memory with AR1 star and 49% of compute, going from 0%, of course, in the first batch to 92% on the last batch. So in the last batch, we use 92% less memory of the cumulative strategy, of course, and then 94% for the compute power.
So the difference between the red and the green is that one you freeze.
Exactly.
The red you freeze all the way. No.
Essentially, for the green one, we freeze both these.
Okay.
And for the AR1 strategy, instead, we just freeze, sorry, the low level generating features. Sorry.
Okay.
I was just trying to.
So unfreezing is better. Right? Unfreezing the linear data is better?
Well, it depends on the particular protocol that you have, for example. In this, if you look at the first protocol where you have still, some in your batch, you still have some representative images for different conditions that you encountered. And in that case, this idea that you're less, let's say, non-IID, you can still improve somehow the performance of your model if you don't freeze the class, let's say, specific features, right? But if you move towards a very difficult non-NID situation, which you have just 300 images very highly correlated of one class, then essentially Air 1 is performing like the CWR approach. Yes, exactly. So we try to fix these essentially. And one last notice is that we lose essentially with these strategies, rehearsal free, we lose like 20% of accuracy with respect to the standard, let's say, idea of taking all these data and training them in a static fashion. So that idea that we used before, the idea that you want to somehow compare that with the pure cumulative approach
It's good, but it's still a big loss.
capacity. Yeah, it's a big loss, and we try to address. To address essentially this issue, closing the gap with latent rehearsal. So the idea in this case is to. Let's move. 1 second. So the idea is that if you really want to solve practically the problem, you can still use rehearsal. But we propose in this paper, it's going to be released soon towards continual learning at the edge. The idea is that we can still be very efficient, and we already deployed this the Air 1 start strategy on an Android application. I was going to show you here, but the idea is that you can be very efficient. You can make this work on an Android phone with 20 seconds of training on that CPU only, and you can do that with reaching a very good level of accuracy when you use also a bit of rehearsal. But as we said before, it's not really useful to use that rehearsal for the low-level generic features. They are very, very good. Them are very good as they have been trained on millions of images with the ImageNet, right? So we try to move essentially that threshold, and we saw that for MobileNet version 1, you reach a particular level kind of in the middle of the network where you can improve any percentage point anymore. So it's actually okay to freeze the network for the lower part, and you can do rehearsal from that particular level in the middle of the network. And essentially, we have a particular strategy in which we somehow store these activations essentially, and then we use them as a new pattern, a new image comes forward, and we concatenate them at batch level so that we can still train in a more, let's say, IID fashion the class-specific discriminating features, and we can essentially recover much of the accuracy we lose when we use just rehearsal-free strategy. So you can see on the left there that with just 1,500 images, that is 1.5% of the entire training set. Sorry. So of all the images that you encounter over time, you can see that we can move from the dashed lines, red and green, to the solid ones, and essentially be with AR1 star be in 10%, let's say, space, so we just distance with respect to the cumulative approach. And essentially, we think that you can actually reach the 85% in this case just by having a more smart way of storing the activations that are more representative for the previous data distribution. Because in this case we just randomly sampled them. But that was not the point of our work, and but in terms of practical applications, I think that's the way to go. Also, for example, storing a couple more images can be helpful. And then on the right here, you can see the difference in performance when you move that particular threshold we talked about before. So if you move the threshold down on the MobileNet versus version 1 architecture, you can see that so from pool 6 to COM5 1.
This is the level that you store the
Exactly. So if you store them very on top of the network, so pool 6, just before the fully connected layer, you can reach essentially 60% accuracy.
Basically, the higher you go, the
Exactly.
poorer results you get, and the lower you go, the better results you get.
And as you can see that at some point you don't improve anymore. So essentially all the lines are squeezed there below 75%. And so the idea is that to cut on that particular level, so you don't improve anymore. So you want to use that particular area, freeze everything below.
What if you retrain it?
No, for efficiency, of course. Then of course, if you retrain from real images, like we have seen there on the left, you get better results. So if you start from real images, you store 1,500 images, you get the best results. But in terms of efficiency, you lose something, but you can work on a much faster and efficient way.
So just to be clear, when you say training those images, you frozen nothing, right? Or you frozen it, but you're feeding the images into the bottom.
So it depends on the strategy, right? But for both of them, we start from the input images. From the CWR, you have everything frozen, but you still start from scratch from the input space. But for the R1, the lower level are frozen, but then you have the class-specific features that are trained.
Okay, but you're still driving it from the little.
Yeah, exactly. Yeah, that's helpful because in these networks we have vector normalization layers, and that it's also very tricky to handle. Essentially, is a layer that tries to normalize the activations based on a batch and layer-wise fashion.
I don't follow.
So essentially, the idea is to converge faster. It was proposed to train the network faster, and it has a few interesting properties in terms of stability of the activations.
Then deep learning.
Yeah, you set the center of the distribution to 0, normalized standardization to 1,
Right.
and that's going to make numeric.
It's an optimization trick, I would say,
You
and
kind of think of it as a conditional, like a numerical thing.
Yeah, it's numeric.
it helps.
Everything in nice
It helps a lot during training on big data sets. In continual learning is much more of an issue, I would say, than it helps. Yeah. Yeah.
So you could switch to layer normalization instead of batch normalization, and that would not be an issue.
Yeah, we did that. It's still very tricky to parameterize, and I mean, it's not easy to work with in general.
So sorry,
Because
why would you need to do layer normalizations? Like these algorithms are not built to build normalized output.
Well,
Output, yes, but in between. Oh, go ahead.
Yeah, because of the value, there's no upper bound on the activation.
yeah, I mean, on top you can put a softmax activation
If you think
function,
about
but
just the output, yeah.
still,
But in the middle there is no. Because the activation function like rel is just a factor that's 0.
I would think that like people would have figured that out just because of numerical issues.
Mhm.
That like I mean like numerical accuracy and like even in, like if you run 64-bit, like you're just limited.
Yeah, it has to do with gradient descent.
Yeah.
If you normalize the outputs, then the gradients tend to get 0 at the edges, and so you don't learn very well.
Right.
And so they did this so that the gradient is always 1, but then the outputs.
Right. Okay.
well, it's
bag of hacks.
right. So just to finish, start a discussion eventually.
3-4 minutes.
Yeah, right. So just I'm gonna skip these and.
That's most interesting.
Yeah, no, I know that you are interested in this, but I already share some details about this with the Subutain, and we can talk maybe later. But just to get to the final points that I wanted to make here.
That was the most interesting part.
You want to
Wow.
if you want that. Well, essentially, we also try to understand how we could somehow reduce the memory overhead of the activations at that particular level in the network, right? So one of the ideas, or the idea there was to of course binarize them, for example, or to essentially have them more sparse. So we did an experiment on the first training batch that you encounter. So just to say, hey, we can do that with these if you want. We tried to have just a simple L2 regularization on the activation.
You change these activations, you make it sparser. You keeping the network architecture the same.
Exactly. So it's the same number of connection, everything. But the only thing that we did in this case was to regularize the activation. So the idea that they are.
Where I was coming from that is it seems to be the right way to do this is, and we've already known that these networks tend to narrow because that's what works well and so on. But if you're going to go sparse, it seems like you wouldn't even have that level fall off at 10% if you made the networks wider. It just might.
Yeah, probably.
Yeah,
We didn't investigate in that this issue.
I would say this is a very, very preliminary.
Yeah,
Yeah.
I'm
There's
just
a lot of
pointing
work
out
to be
that,
done here.
that, you know, sparsity in some sense should not reduce any loss in accuracy if you have the right number of units and the right sparsity level. I mean, just, you know, this system can run with 5% sparsity and do very well, but you have to have enough units to do that. So I just be careful to over-interpret that.
Yeah.
I'm not sure if I can read this. What are non-zero activations? And
So essentially, we focus our attention on a particular layer on the network, and then what we are looking at is the number of non-zero units. So essentially,
right, but how is that different from the alpha value? That's sparsity.
so alpha value, sorry, alpha value is the regularization parameter that we use to force,
that you are specifying, in fact.
Exactly,
Okay.
exactly. And then the impact on this specification on the accuracy.
Right. Okay. Now I can read it.
Yeah, it's a bit. Sorry,
Yeah, the y-axis is double duty.
Yeah.
Exactly. That's what was.
I didn't catch that.
Yeah, I see it's both the number of percentage of activations and the test accuracy. So sorry for the.
So it was like a balanced 50-50 distribution before, and then like with the alpha value actually specifies this.
Yeah.
And then that has an effect on the.
Yeah, and then you can see that you can go from 10% to see more than 50%, and essentially you keep the intact the accuracy level. And we will discuss this in much greater details in the upcoming Journal Club issue on selfless continual learning.
Quick question, why should start above 50? If you're using batch power 12, what is the equation above?
Yeah, that's standard. This was a training on the first batch of the entire thing on core 50. So the idea is that just pure cross-entry optimization here, you have essentially that kind of activity, and it is in line with other works we have seen on MobileNet. So it just as it is normally. So just to finish, on the future, we are trying to change this idea of storing also. I won't talk about all this stuff, but just on the idea that we want to change essentially this entire architecture so that we generate back the activations, not just store them from the past. So that would be a nice advancement. We were trying to work on this direction, and with the idea that essentially you train incrementally the generative model. You are subject to catastrophic forgetting as well, but the idea is that you want to relearn this very little model. I don't know, a variational autoencoder or something like that. On that particular space is very little, and essentially you generate and learn again from both the generated images, activations in this case, and as well the actual activation from real world images that you get from the streaming sensory data. And we would like to move in these directions. And I don't know if there are some interesting points in this architecture that you think are can be somehow interesting to try within the cortical learning algorithm implementations, or where it can help.
Can I ask something?
Thank you.
How do you avoid turning the stability plasticity dilemma into metastability metaplasticity dilemma? Like you are updating your plasticity value, right? So not the value of the weight, but the importance of it, right? And so how do you avoid that when you are learning that? Like you somehow have to integrate, right, the metaplasticity of the past with the metaplasticity of the future. And so if you're learning a lot, some weights that did not used to be important are now important, and some weights that did not used to be important, you know, like the other way around. So, but that is reflecting what? Recent data, the whole batch. How do you integrate that? Do you have an exponential moving average? Do you transfer that across time? It's still not clear to me. Like the algorithm that you showed did not explain that.
So I don't know if I understood the question correctly, but essentially, as we think that we see that the network capacity is good enough to maintain all this information into its memory, into its parameters.
Right.
The assumption is that everything is important, and you want to encode everything continuously, right? So for now, much of these strategies, they assume that you can encode this information and preserve it in some weights. And then you can accumulate all this stuff together, and hopefully that will lead to generalization as well. But that's I think the assumption that is made more often in this context, and I agree that I mean it should be
I think
much
you're
more
not addressing my question. You are computing not just the right.
I think your question is asking how do you assure the primacy of the hyper
parameters? Yes.
Over the original ones.
Right. How do the primacy recency curves look?
the prime.
In other words, if they're both correlated,
Okay.
then they interact in some complex way. What he's asking is, how does your technique maybe abstract it up to that hyper level and not still have the complexity of the lower learned weight and importance of the weights? So he's trying to say, have you actually made, a distinctive step by defining these hyperparameters?
No, actually no.
I mean, how do they get updated? You have one batch and then another batch and another batch, right? And in every batch, you're not just computing the weight, but also the importance of a weight.
Yeah.
How does the importance of weights earlier change now with the importance of the weights now?
Yeah, I mean,
how does that update work?
I mean, it depends on the approaches, of course, that you find. Some people just they don't fuse them somehow. So it's a fixed factor. So you encounter them, you weight them with a particular hyperparameter, and that's it. What we
weight them with a particular hyperparameter.
So you have for example,
is it an exponential moving average?
No.
Are you just summing them?
Yeah, exactly. So the idea is that you want to weight them somehow. And for most of the experiments that we did, and the people in this community are doing, it's maintaining these parameters the same for all the possible regularization term or training batches that you're encountering, right?
Right. A, I still don't understand what the value of that would be, and B, I still don't understand how you actually update your metaplasticity value. Like, what is the computation that is being done?
It's the model better.
Well, yeah, I mean, as in many, I mean, it's experiment.
Just give me an example, because I can't fathom it, right? Like, how are you going to update your metaplasticity without running into problem of catastrophic forgetting, not, through weights that overload each other, but metaplasticity values that overload each other? Okay,
so we don't have explicit meta learning parameters, right? We just have hyperparameters that regulate somehow the.
I think he's saying that he has a hyperparameter that controls them.
Yeah, exactly. We don't have a learning partner. It's not a learned parameter there.
It's like when you said the learning rate in a model.
Exactly.
It's a So he's leveraging with a scalar value.
Yeah.
The whole thing, it's not like, so you have all the detailed stuff down here, then you have this thing up here, which is basically saying, yeah, what's our forgetting rate? What's our update rate?
Oh, so then this is a lot more trivial than I thought.
Yeah.
So you're not storing, you're not actually doubling
it
memory
is.
capacity by having a synaptic weight and a permanence value.
No.
No. You just have a global plasticity, which can be high or low, which you.
That was that Fisher matrix he was talking about.
Right.
Correctly, yeah.
Okay, well, that definitely means, okay, it's a, right. Yeah, I don't follow what the true power of this approach is here. Yeah, I was under the impression that we're talking a fancy scheme of metaplasticity here, but that's not the case at all.
I think
It's just a simple up or down of plasticity.
The tests only have, I think, 8 different tests. The test we're running here, we only have like 8 different distributions, right? If you were to increase that number to, let's say, 1,000 distributions, how would that same scheme hold? What do you think?
Well, I don't think this whole idea of learning by consolidation, simply as it is, can hold for longer periods and different tasks and different distributions. It's going to change more smoothly and with a better, also maybe integration of meta learning strategies. There's a lot of discussion about this integration of continual learning and meta learning as well. So we'll see about that. But as up to now, it's already super tough to work in this context. It's difficult to also in terms of experimental, terms, and there's still a few utilities and benchmarks and tools that you can use to work directly on continual learning. So it's early days I think in continual learning, and we are moving. Still trying to maintain, a good level of application possibilities.
I see what Florian's saying would be an evident problem when we try to increase the number of tests. And we catastrophic forget also the hybrid parameters.
Right.
Could I ask, on what basis are you going to create a generative model? You've got these featured, whatever,
Yeah.
here. I mean, I don't know what approach you would use to what the model would be for that.
We are trying to work with a variation autoencoder at that level.
Okay.
We are in the process of moving from the first MNIST, assessment that is working very well on the activations of core 50 in this particular protocol and see how it goes. But the idea is to work maybe with that articulation, maybe convolutional. But we'll see if that's the case and if it's useful. It's a work in progress. We'll see about that.
Because I'm just wondering, what's your feedback on that model, saying that, yeah, this is within the space of that red box.
Yeah.
But, are we comparing it, we're feeding it through and saying, hey, did we get anything that's approaching something that's real? But we don't have ground truth down here to run it through, so.
Yeah, no, the idea of estimating how well we are reproducing essentially these activations is to essentially switch the real one with the, let's say, generated one and see in classification how you can go. So essentially
I mean, if this thing is generating the thing, you don't know what the ground truth for that was. So.
You can try with real images and see what are the activations, right?
Right, well, you can feed it down here, but what is that? Whatever you hallucinate in this model has no relationship to down here.
No, with the inputs, not anymore, but you can somehow try to learn, for example, you take the static scenario in which you have all the training images, right? You try to reproduce these activations back with, I don't know if, for example, in the end, it doesn't have the encoder from the image. This is what we are saying, right? But it has the right encoder from the activation that is the ground truth at this point.
Right, but then you're saying, I'm going to take that perturb it, and let's arbitrary, let's say this thing, I recognize the cat.
Yeah,
So I'm going to do a perturbation at this level. Do I still get a cat? Is that
exactly. That's the reference for the work, right? You want to essentially substitute the real activations with the generated ones and see if the information is retained within that particular low-level dimensionality that it is in
just with
model.
the forgeries that are around? You could be adding noise to the thing.
Yeah.
That I created an activation, but it could have been the same thing as if I fed an armadillo up there. It's still recognizing it as a cat, so good.
No, you're right. You're right. Maybe we should run also these tests to see, not just on the accuracy level, see how everything is going up there.
Right, yeah, because you're hallucinating both perturbations, but you're also making a pretty large leap as to what your ground truth could be for that thing. Now, in principle, if you could learn the structure of that box and say, I can find the cutting planes between this as long as I perturb within there. I mean, that is something that is fathomable. That would be really cool. I mean, you're showing a nice picture there. Everything categorized.
That's a representation of the MNIST using also, I think, a variation autoencoder, but plotting in 2 dimensions. No, a TSNet maybe is that. However, you can always find some very nice representation starting from the encoder of the generator.
But that is just the PCA. Like,
No, I think that's a picture from TSNI from the Google platform from visualization from NIST. It's a 3D visualization, you can rotate or something like that. But it was it's not just an image taken from Google,
So what level of evidence is it pulled from?
I think that is I don't want to.
Okay.
I don't really know.
Okay, I was just curious. All right, fine.
Okay.
So this is, I'm thinking about how the brain does all this stuff. It's completely different. And I don't know if you care. I mean, maybe the task is to do continuous learning and deep learning networks, and then that's the thing you're going to do. In my mind, I'm listening to this whole thing, and I'm trying to figure out how to explain to people the fundamental ways that brains do this differently. And sometimes, I want to talk about that, but I'm not sure it's important. But given that you're here, I figure it must be somewhat important to you.
Yeah, exactly. No, for me, it's important. It's something that I would like to see more and more integrated in this.
So I will try, if you don't mind, I'll take a minute.
Yeah.
And try to give you, and I'm making some of this up right now, so I could be getting it wrong, I could be making mistakes. I always try to oversimplify things. I try to make the simplest explanation I can, and sometimes I miss some details. But here's my simple view of this. And correct me, if anyone who wants to correct me if I make a mistake, please do. You got sort of 2 worlds here. The world of machine learning starts out with you want to represent something, you have a bunch of units in a layer. And all these units have some activation, they're all participating, right? So this is in a deep learning, deep network, you have, there's no sparsity in some sense, right? And so I have some sort of precise, to represent different things. If we're going to represent different things here, I have to have very precise activation values.
Yeah, particularly if you want to learn digital data, which is 50% active.
Was that?
I mean, but digital data, right? I mean, whatever it is.
Well, I'm just saying,
from
classically, you have a bunch of units, they have some scalar activation.
Yeah.
At the one extreme, they're all active to someone else, right? And so to represent different things, you have to have if you want to represent a lot of things, you have to have fairly precise activation values here. And now the basic problem is you want to associate one set of units with another set of units by some weights here, right? And since all these units are active in some sense, and all these units are active in some sense, and you have some full connectivity matrix, then the actual individual synapses here have to be pretty precise too. And you have to be positive and negative because they're trying to tease out all these different patterns from that. And so that's the problem with continuously learning, deep learning, continuous learning here is because to get the whole system to work, to differentiate these different input patterns and these patterns and get them to associate correctly, you have to have very precise numbers here.
Yeah.
You have to train it over and over and over again to get there. Where in the brain, you end up with units, but many more units. I don't think much interesting happens in the brain without 10,000 units, 10,000 neurons in a layer, right? I don't know what your typical deep learning network is, it's not 10,000. And then we have a sparse representation. So we might have 2%. So if I have 2% of these cells active, I have 200 units active. And of course, now I can go completely binary because I can pick 200 out of 10,000 all day long. I can pick millions and millions and millions of them, and they'll all be very different. They have a minimal overlap, right? They'll average about 4 units per one. And so I can pick a million units here, not worry about the activation levels, and every one of those will be almost orthogonal to each other because they're all going to overlap roughly about 4 units, and they won't. Even if I pick a billion of these things, you won't find 2 that are overlapping by 100 units. It's not going to happen. So the representational capacity here comes from the sparsity, not from the unit values. And I have an almost infinite representational capacity. It's very simple. It's dumb. And now I want to correspond that to another 10,000 units. And this is also going to be very sparse. And so on these units, they only have to make a connection to some. Maybe we've shown 20 of these 200. You just have to make a connection to 20 of those, and this guy will get that pattern perfectly. Now here, every unit is going to participate 5% of the time. I mean, 1 out of 50 times, 2% of the time. So 1 out of every 50 patterns. That's not a problem, but it is a problem when you make these connections. Because if a unit's trying to represent, if the unit's going to participate every 50 patterns, I want to represent 1 million things, 100,000 things, the synapses will start conflicting with each other. So what neurons do is they have multiple branches. So now an individual cell, instead of, you can say, well, it's going to participate in 1 out of 50 representations. And it has to recognize a lot of things down here, but by breaking it out this way, my synapses aren't going to get confused. So you can just do sort of a rough calculation. You can say, well, this, if a unit has 100 branches, this cell is going to be activated, 1 out of 50 times, and then I'm going to multiply that times 100. So basically, I get 1 out of 5,000. This thing can make 1 out of 5,000 patterns here without getting confused, type of thing. And at some point, they start getting confused. At some point, you start training the system too much. You run out of these dendrites, and the system starts to fail. And that's how our systems start to fail too. So we train their sequence memory, and after 800,000 elements and sequences, the sequence memory starts failing. And the way it fails is it fails, in some sense, not catastrophically. What will happen? It fails that you're trying to map unique patterns here to unique patterns here, and what eventually happens is you start mapping multiple patterns here into single patterns here. So you start to generalize. You start to say, well, they're all the same. The example I used to use is when I first started seeing plays in my life, theater plays. I remember every one. I saw this do with my daughters too. But after you've seen several hundred of them, they kind of blur together, and that becomes, oh yeah, that's sort of like a no-power play. I mean, that's one of those dancicles. That's one of these, and you can't remember the details. So it fails nicely. It's not a catastrophic failure, it's just generalizes. Anyway, so the way I view this is that by sparsity and by using sparsity in large number of units, high sparsity, and multiple dendrites, where you essentially can train. You're essentially training. It's as if there was many unique systems that. And I learned dogs, and I learned armadillos. They're like completely separate systems. They just overlap so little that you ignore the other one. That's why you can do incremental learning. You just add more, and it creates a whole new world for it.
I think one way, if I may interject, I think one way of getting to that is, I think you very nicely mentioned that in case of the sort of like the 50% activation, right, the binary code, right, which on average uses half of all the bits in any given encoding, right? It's built that way to be balanced. you get this very tight requirements on the fine tuning of the weights, right?
Yeah.
In the sense that if the weight value is 5% larger or less, like the network starts failing.
Here's what you can think about that.
And there it's super robust. It's just a binary state. There's weight or no weight.
Yeah,
right?
yeah.
That is already like all the
The
information.
key here is that I can recognize this pattern absolutely certainly if I just make connections to 20 of these guys.
Right.
If I make connections to 20 of these, 50, there's 50% of these, and I make connections to 20 or some 20 of these, I'm going to get a lot of errors. It's because this is denser. Yeah, so it all plays on each other, and it's super robust. You get binary weights and binary activations. It all revolves around sparsity, and then you get this additional huge multiplier by the dendritic segments. It gets even more complicated than that, or even better than that, because we now know that in the cortex, we're learning these three-dimensional models, and so we're assigning sort of things to locations or in reference frames, and so it sort of multiplies on itself. You can create all these unique things because nothing ever interacts. In fact, we have more of a problem in our models getting the system to generalize than we do getting to. It's like you can learn all day long. And you can do continuous learning and learn all these things, and it all works great. The harder part is the generalization, because here we've separated everything else. It's like literally when you do it this way, it's like you have 1,000 different systems, and they don't interact with each other, so they don't get confused.
Yeah, but that was one of the main arguments, I guess, behind deep learning. The idea that you can reuse features, you can have them, generalize more and more in an abstract form. So that was the main argument. That's why.
Well, I don't think that's not why deep learning came about. That's deep learning was just trying to get neural networks to do anything. But I mean that is an advantage of it. There are, so we talked about the generalization side. So it goes to the other extreme, right? So here we got these systems that you can learn continuously. They're very robust. They're very simple. They have simple weights, simple activation states, and nothing gets confused. And then the generalization is the issue. And so we've spent a lot of time here talking about generalization. It's a much more complex topic, but in the brain, you don't see networks like this that are just layers and layers and layers, right? And so I could get into it, but maybe another day that, it's a much more complex idea of what makes generalization. And I actually think it's very much tied to attention. The way I can say it is they see two objects, or you've learned a bunch of objects, and now you see a new one. Let's put it that way. You've learned a whole bunch of objects in the world visually. Let's say visually, and now you see a new one, and you're trying to figure out what the hell the new one does, or what is it good for. It's got to be immediately. It's like, what the hell is that weird thing? And what you end up doing when you have this kind of weird little object out here that you don't really know what it is at all. What you do is you can just observe yourself doing it. You start attending to sub pieces of it, and as you attend to sub pieces of it, as you go from attention to attention to attention, the brain is literally representing the position of these sub features relative to each other, and then it might represent a different set of sub features relative to each other. And as you do that, it says, "Oh, I've seen that subset of features somewhere else before." And so I don't recognize the whole thing and say, "Oh, that must be a new type of can opener." You say, "Oh, these three features here suggest it's similar to other objects that have had those three sub-features, and therefore this could be part of a can. It could be similar to a can opener." If I look at these three features, I go, "Oh, no, that could be part of a new phone," or something like that. And so you by attending the subset, you generalize to other systems that have those subsets. But it's a much more meta process. It's more of an architectural meta process than we could get in a deep learning method. So again, I found it. I'm saying this because it's useful for me to practice talking about these things. Just trying to really clearly articulate or try to articulate the difference between what you get with a sparse network like you see in the brain and what you get with the sort of the more denser networks, and why it's harder. What do we have? If you really want to get to that, you have to go over this way, I think. Yeah. But when you get over this way, then you have the generalization issue, and then you have to do more stuff, complicated stuff like this. But that's it's just interesting. I don't know. I'm just looking at the world.
It's what I'm trying to do as well. So
Yeah.
the other way around.
The question is, I always, remember we drew the bridge on the board the other day? And I'm like, are you trying to get these networks to work that way? Or are you trying to like solve these problems using these networks?
I think I'm going the other way around. The idea that you can distill some ideas that maybe you develop here and put that inside the current deployed neural networks to see if you can go to.
I don't know, in the current work we're doing right now, the stuff we're doing here, I don't know, are we actually increasing the size of these network layers, or are we keeping them the same? You're not saying.
No, but I think it's still, for example, the layer I was talking about before, I think is 32K of neurons activation.
Is that right? That's pretty big.
No, these networks are kind of big now, so
they're already
And they're
super.
already big, so we don't have to increase the size.
it's just about
Well,
improving.
the RAIN guys were here, and they were talking about how the dimensionality of the networks are narrow and tall because the GPUs can't really handle wide ones.
Right. So,
I had the impression they were smaller than 32K, but am I wrong about that?
but actually, today, state of the art, we also use wide and slightly shorter networks, so somewhere in between. So at some point, we're doing very deep and narrow, but right now we have like wide.
So that comment from the RAIN guy was not.
Well, are you saying each layer has 32,000?
For
Or
example, a convolutional layer that has several feature maps and so on and so forth. The activation that you have is in total 32,000.
okay, so the output of a convolutional layer.
Yes,
is 30,
yes.
Okay.
And it kind of depends on when you put yourself, of course, right?
Can I-
Because if you have
I didn't know they were that big.
even
That's
bigger,
bigger? I mean, 32,000 is big. I mean, we don't need that many. You can do this whole damn thing in a quarter of a column with 10,000 nodes per layer.
Yeah.
Because this is infinite. This is
When I
infinite
think about
capacity here.
what makes my networks expensive, right? It's never the units.
Mm.
It's always the plasticity, it's the number of synapses.
Yeah.
And the ways that synapses get expensive is through the numbers that are needed for describing them. And if you have structure plasticity like that, it's just a bit, right? 0, 1. Whereas here, these are 32-bit, 64-bit
Yeah.
values.
Yeah.
There are things in between, and personally, my view is that in biology, we're actually in between. Like the synaptic values are not 0 or 1, right? Because there is such a thing as potentiation. But it might just be a 3-bit discriminator, right? And people have tried to estimate, right, how much storage capacity a synapse has.
But
right?
we must have had this argument before, I just don't remember, but given that synapses are largely stochastic, you can't rely on any precision.
Right.
And so, so I can achieve the whole thing with binary, great.
Right.
It's a 3-bit synapse is meaningless if it's stochastic. It's a stochastic binary synapse. So it's different. A little bit more stochasticity. Anyway, I think, obviously we go to binary because it's simple, but we also do it because we think it's not going to make a difference.
Right.
And so that why not? I didn't realize that they were that big, these layers. I had the impression, from some previous talks, maybe they used to be now.
So what we're using now only has the biggest layer has up to 4,000 activities.
Oh, that's small.
That's what.
Well, you just told me there's 32,000.
It depends.
Simulations, his simulations.
Alright.
The 32,000, 4,000.
Okay. Oh, so the work we are doing is small.
It's big because if you got 400 channels in a 2x2 filter, that's 4,500 base. But how do you get 32,000?
I mean, I can check. I have then we can check. No, we can check. But the idea is that many networks you have the volumes after each layer that can change over the depth of the network. And for example, for MobileNet 1, you start small and you grow and then you go small again. So the idea that you create, you try to. In that case, that's wise, but I don't think it has an impact on the kind of activation or volume. So the idea is that
32,000 is per one layer or per total number?
one layer, one volume.
One layer
If you consider all the volume of the activations, that's volume. Like in this case, you talk about volumes in general because you want to distinguish the. I mean, it's still a let's say you start with a 3D volume on an image is a tensor. weight and channels,
Oh,
right?
that's that volume you're talking about.
That kind of
That
then
volume.
then you can change
But
that.
once you're in the network, it's just a bunch of units, right? It's not really volume.
But they'll still, especially for convolution neural networks, they can.
They're
It's
thinking about the
useful to.
convolutional layer.
Yeah, it's
They're
useful
gonna do
to
that
consider.
cheat, which is sort of a cheat, to achieve what,
Yeah.
you know, it's not, it's a cheat that does what brains do through just quick learning. Fine, okay, so, you know, interesting, and the kind of networks we do, making it bigger increases the capacity, and as long as you got enough active units, you're good. The problem in the brain is if you make the number of units much larger, if I go from 10,000 to 100,000 and I keep 200 active units, it gets too hard for these neurons to find the active units down here to connect to. So there's this balance in biology, there's a balance between like potential synapses, like I need to be able to find 20 good synapses, and you make this too sparse, it's just impossible to do. But in a software, you can make this really big and you can just pick 20 out of the active units. So that's an area I don't think we really explored much, because we haven't really talked about this, exactly these kind of units before, these kind of models. But this could be made much larger and sparser as long as you have the right number of active units and the capacity of the network goes up.
I mean, 90% of the brain's weight is connectivity, not
Yeah.
not actually the
Is that really by weight? I didn't
Well, it
know.
depends on how exactly you measure, but if you
Yeah.
just measure, for example, gray matter versus
Oh,
white
yeah,
matter,
yeah.
which is the actual
Okay.
cells,
So,
right, on the
white
surface.
matter also has the, you know, the myelin sheath and fats and all.
Right,
that.
sure, and those are swan cells, but they don't do information processing. So you can think of it as just the connecting fibers, right?
Yeah.
And so the brain is really just, I mean, like, you know, I think that you just put it right with talking about the connectome all the time, because
Yeah.
it's mostly a connectome.
I think the number I saw, there's 2 kilometers of neural pigment, axons and dendrites in every cubic millimeter.
Right. Yeah, that is a good way of illustrating that point, right?
Yeah.
Is it kilometers per cubic millimeter?
Yeah.
Wow.
Yeah, it's, you know, you think that's almost impossible, but then you still quickly do the math and say, well, you know, these things are maybe about a micron diameter, and you just start thinking, it actually fits. It's surprising, right?
Yeah. Can several times around the equator with the entire wiring of your brain.
Yeah.
No problem.
So these things are really small. We don't have a good intuition how things, when we have small things, how what they look like.
One of the differences, I mean, because almost all the deep learning right now is with these convolutional layers. So what we have in the brain is effectively.
Well, wait, is that true that it's not, is it the convolution you're saying, or is it just the network, the connection between them?
I would say, in other words, each one spans to a localized region. They're not fully connected.
Yeah, of course.
So,
Yeah.
I'm just saying, what you illustrated there was potentially starting off, you have fully connected layers. On the networks that you have in machine learning, the fully connected only comes at the very end.
But now, what I'm talking about here, in the neocortex, if you look at the neocortex, and we're talking maybe like a millimeter or a half a millimeter, let's say 1 millimeter. We're talking about, you know, a group of cells in 1 millimeter there, right? We're not talking about the whole brain. We're just talking about the connections between these layers in one column. And there's 150,000 of these columns in your brain. And so now, if we want to talk about, if we want to talk about that, the next other region in some sense, then there's this convergence going on, which is what you're referring to there. I'm just talking about within one teeny little section of their cortex, the connectivity there. There is this sort of hierarchical, sort of semi-hierarchical connections going on. But you know, the bottom line of that is, if you think about a convolutional deep learning network, they're passing some representation to some representation, you know, like features to more features and more features. What we think is going on in the cortex is that each column here is actually is building a representation of a complete sensory motor learning object space. It's more than a feature. It's a structure. It's a 3-dimensional structure in the world. And now you're building compositions of 3-dimensional structures, which is far more efficient than just features.
Right, what I was actually going with that is that in the cortical layers that you described, that you have lateral connections, those don't exist in convolutional layers as such.
No, I'm saying, what I'm saying in the column here, if I look at all these columns here, you don't see a lot of connections going this way. right? So it's almost like a convolutional layer. It's like you're saying, in some sense, in a neural network, they replace this entire column with one neuron. And so if you take every neuron in a convolutional neural network and replace it with 100,000 neurons of the column, then you got sort of the equivalent. And if you think about it that way, then yes, all the connections are this way. But so it's just this computational unit here, which is so much more complicated than this computational unit.
Okay, so let me get to the third thing I was trying to say, on that. When they originally started out, there were these things called Boltzmann's machines, which were untrainable because they had lateral connections. It's only when they went to restricted Boltzmann machines that they could actually train them. Okay, potentially you have Boltzmann machines in the cortical columns in some representational form, which we've not addressed yet in machine learning.
Yeah, it's a way of thinking about it. I have to go back and look at, I mean, it's been a long time since I read the literature of Boltzmann machines and restricted Boltzmann machines.
Well,
I don't think about it that way. I'm thinking like, I'm thinking about it like, oh, we have representations for location and orientation and,
I understand that in terms of architecture, that's one distinction where the current machine learning is not mapping to coming close to what you were describing.
Well, let's take our sequence memory, right? The HGM sequence memory. That is literally, you can implement that with one layer of cells with 10,000 neurons. Is organized in mini columns, and in some sense they're not fully connected, but any cell could connect to any other cell, right?
And that's Boltzmann.
Well, you can call it a Boltzmann machine. I don't know if it still applies when these connections are learned and there's a structure behind it. It's not like there's this fully connected network and I'm just trying to adjust the weights.
Right.
I'm not sure it really applies anymore. I don't know enough about Boltzmann machines to
I would
say.
say necessary, maybe not sufficient condition in the description, but in architecture, since we don't have those cross connections in the normal convolutional layers in the restricted Boltzmann machines, we don't have the potential for some of what you're talking about.
Okay, maybe one way of looking at it, yes.
Yeah. I mean, basically, in a restricted Boltzmann machine, you have the connections are only to the next layer, not any cross connection.
Yeah.
So,
but the idea of a Boltzmann machine was like, this sort of amorphous, highly connected network, and how you're supposed to train it, built with point neurons.
when there's lateral connections.
I know, but we're starting with this very complex structure that doesn't exist in a Boltzmann machine. We start with the assumption that there's these mini columns. We start with the assumption that mini columns are inhibiting each other.
You're imposing some order on that.
Yeah, and so at some point, to me, it doesn't become useful to call it as a Boltzmann machine because the Boltzmann machine has a whole bunch of legacy with it
It's just a term that you can talk to with machine learning.
I know, but I think it would be misleading. It might be misleading because they'll say, oh, I know all about Boltzmann machines, and then they will miss the whole point.
Okay, let's put it this way. You're saying that what we have is different than a restricted Boltzmann machine. You might want to call it, something between the two, but in the sense that unless you move away from those, you can't model in a topological sense what we're trying to do.
I think maybe that was what on the very first slide Vincenzo set up. We used what was the bottom line oval called? The structural architectural, right? Yeah. To me, it's like, oh, the brain is all about architectural things, right? The mini columns are architectural. The inhibitory neurons are architectural. There's a huge implied, neural networks are just like point neurons connected to point neurons, and blah. And here we have all this intricate detail that does stuff that imposes algorithms on top of how these neurons work and who they connect to and what they do. And that's completely missing from the deep learning network. So it's like, again, the way to think about it, in a deep learning network, something there's one neuron is in the cortical column, is in the neocortex, it's just 100,000 neurons, literally 100,000 neurons is doing what deep learning networks are done with one neuron. So it's going to be a much more complex function.
I mean, I think people who are in machine learning think that their networks have a lot of structure because they say they have layers, and that is their structure, right?
Yeah. Well,
it's a far cry from the amount of structure that we would find in a cortical layer.
And so, well, a lot of them are thinking that those layers correspond to the, in the cortex, you got, they got V1,
regions.
and then you got V2, and then you got V4, and then you've got, IT, that kind of thing. They say, oh yeah, our layers are just like that. Well, it's interesting because in the brain, very sophisticated object recognition occurs here, just 2 or 3 levels up, and where you have to go 100 levels, those things. But my point is that these levels are just so much more complicated than what those levels are. 100,000 times more complicated. And so, yeah, they think they're mimicking this, but as Supertype points out, these are like 1% of the connections in the brain. Or less than 1%.
This time counting reverse connections.
Oh yeah, reverse connections.
Which also dominate over feed forward.
Yeah, there's 10 times as many going backwards, and of course the feed forward connections. There's multiple pathways. There's one that goes through the thalamus, and the thalamus does something. I mean, it's really complicated. So it's not to say there's anything wrong with learning deep learning networks. Just if you want to, it's really good to know why it is that the brain doesn't have a continuous learning problem.
Exactly.
Yeah. So. Anyway, it's how to bring these worlds together is the challenge we have.
Yeah, it's a very good challenge, and but it's very interesting because I think that many ideas are, shared among the two fields, even though maybe you don't think so. But I think that many ideas have been going around also in machine learning about this, and it's just a problem. Most of the times, it's the problem of mapping ideas, right?
Yeah.
So that you have a different language, you have different histories.
There's a continuing problem. I just read a book this weekend that was sent. It must have just come out, but the publisher sent it to me. It was by Gary Marcus and Ernst Davis, and it's called Rebooting
AI.
And they're basically like, yeah, deep learning networks are great, but here's all the problems with them. Here's why they're not on the path of machine intelligence. And they ultimately make the argument we need to go back to the old-fashioned AI with, knowledge
rules and expert systems.
Expert systems.
Yes, but they have a little section where they talk about the brain, and they say, the typical version, this is a very classic view. They say, well, the brain's really, really complicated, and it's so messy. It probably doesn't really have any sort of regular things to it. It's just a bunch of stuff.
Why bother?
Why bother? It's like, so we can observe some things at more of a sort of cognitive level or psychology level about like how children learn and so on.
And Marcus is a cognitive scientist.
And so both those guys, I think, come from that world originally, right? The linguists and so on. Whereas we need to get people. So even when AI researchers say yes, we can think about the brain a bit and be inspired by it, almost nobody wants to get down to the details that we're talking about here. So that's a problem for us because I think those details are going to be essential.
Yeah, but how does one fix that, right? How does one get good at communicating? I mean, like to some sense, obviously you need how does one teach in general, right? But how do you also get people interested? And I think to that extent, you really need, maybe visualizations are going to do that.
Maybe writing books going to do that. Maybe more. Maybe having our research meetings online going to do that. It's interesting if you go back, and so a long time ago, I realized the problem we have here, the communications problem.
Right.
And you go back and you look at the history of scientific discoveries, like tectonics, for example, right? How many decades did it take for the guys who understood that that's how the Earth works to get other people to understand that's how the Earth works? Right. And so, I look for lessons in those things. I go back and I read all these different stories, like how did this get about? How did this come about? And it wasn't terribly encouraging.
Right.
So, but we can do better. I'm not daunted by it, right? I think part of our challenge is the communications challenge, and that's why Matt does what he does, and that's why the research we do, and that's why I'm writing a book again. And we keep plugging away at it until.
That's why we live stream.
Yeah.
It's a big part of my job.
maybe you.
By the way, like my idea.
Communicate some of it. Although for me, it's going to be like a little bit, more likely a little bit the other way around, like me communicating, some of this need for general principles to neuroscientists who want to drill down on even more tiny little bit of detail and care about every little.
But as you and I discussed, most neuroscientists don't really want to think about like what is the function of a cortical column.
Right.
They just don't even know where to begin.
Right. They'd much rather investigate this one protein cascade that they now found, which is not understood.
Well, one of the problem is that the interesting things are all emergent phenomena. You have to put a lot of these things together and balance them right, and then you start getting interesting things.
But I'm going to challenge you on that, Kevin, because we just talked about how you could just take the concept of sparsity and talk about its benefits. And then you can take the sparsity plus active dendrites and talk about its benefits. So I think it's not like you have to have all this stuff and then bingo, it happens. I think we're trying here to show that there's somewhat of a step-by-step path. And so you could just talk about the benefit of sparsity and not anything else, and it's still meaningful.
Right.
So
that's the hope of this endeavor, right? That when you can show that for one little thing already, look, here's an idea that you can transfer and it might prove useful. That you then get people interested in, okay, what are the other many what is the next one, right?
No, I understand sparsity is the tease, but generally I'm just describing the problem of communication is that it's one of proof, because you can't look at this thing and deduce that you're going to get these behaviors.
No, but
They're emergent, and
I'm going to push back on that too. I'm sorry. I don't need proof to know that the cortical column is living century motor miles of the world. I have enough evidence, and that when you deduce certain principles of it, you know it's going to be right. I wrote a little section about this because people say, well, you can make up this stuff all day long. How do you know? And the answer is, if you're satisfying a whole series of constraints. We have all these constraints: the anatomy of the cortical column, and the physiology of neurons, and the functional things we know. You have all these constraints, and if you come up with a theory that satisfies any number of constraints, you're pretty much guaranteed it's right. And the problem is other people don't have those constraints. They don't know them. So you just say, oh, a cortical column does X, and they'll say, well, how did you know? You just made that up. And the answer is no, I can be 100% certain that that's basically right, because So I don't think you have to prove this stuff. So for me, at least, for many people, that's the case. But for me, at least, I don't need the experimental evidence to prove all this stuff. We have so much experimental evidence already that is unassimilated into theory. That if you can assimilate it into a theory, in the analogy that Don came up with, it's like solving 10 or 15 different words intersecting in a crossword puzzle. You solve all these constraints at the same time. You're pretty much certain you got the right answer. But if you just solve one of those, you won't get it right.
Well, my point was not to disagree with the basic validity of things. My point was in terms of get the perception of it.
Well, so here's how I would do it. It's going to take years to get experimental proof for all of this stuff. Some of it's happening already, like we're seeing fMRI studies that show grid cells in the cortex. But if you can educate people about those constraints, if you can educate them about the entire problem and all the things that must happen, then I'm hoping other people will see it the same way that we see it. They will look at it and go, oh yeah, I guess that has to be the way it is. And
I'm not saying you should be doing anything different than what you're doing right
Yeah.
now. I'm just putting a label on why it is difficult to have a paradigm shift on this thing.
yeah, so the challenge is, to me, is not wait for experimental proof. The challenge is how do we give people enough of the background information, enough of the constraints, so that when you present the solution, they also say, oh, I see, that really is the only way you could do this. I mean, to me now it's become so second nature that our model of the world is built on reference frames, and that everything has a location. Just the fact that I see you over there tells me that there's neurons representing your distance from you. That has to be. What else? How else could it be? So my hope, Kevin, my hope is that by describing the problem and walking through all the constraints of it, that people can also come to the conclusion and say, oh, that makes sense. It's got to be right. Otherwise, if you just throw out the answer, they'll say, well, one idea.
Yeah, for me, it's almost all about the language, right? If you want to talk to someone, you need to speak his language. So it's often when I read Numenta papers and something like that, I still feel there is a gap with respect to the machine learning world in
Yeah, I
terms of
think you're
vocabulary,
probably right.
everything. So actually, people listen to things that are rational in the sense that you have A, B, you can understand now C, but you still have to understand the language and all these things in a way that's understandable. That's,
Shortly, within a month probably, I'll have the first half of my book written, and you can all read it. And it would be very helpful to have critique on that as to how good a job I did trying to span the language problem or describe the problem in a way that a machine learning person would say, oh, I can follow that, I can follow that, I can follow that. Yeah.
absolutely.
Yeah, that matters. Yeah.
I agree with that.
Engine is key.
Totally.
Because
I don't know if anyone presents something, the first thing I do is start asking about your work.
yeah,
I did that today, right? What did you mean by that word? What did you mean by that word?
exactly.
It's just like crazy. And that, that's again, like the Boltzmann machine, like, well, you're right, Kevin. It's a sort of a derivative of Boltzmann machine. But if I say that word, then machine learning people are going to assume they know what it is.
Yeah.
And they're going to be wrong.
Well, they're gonna assume it's unworkable if they can't do it.
Yeah, you're right. And so I don't want to mention that. I want to bring them into my world as opposed to like,
Okay, well, then you're gonna have to admit language for what the structure of this thing is.
well, we're trying to do that, right? We're and not just language, but also metaphors.
Right, well, pictures are helpful.
Pictures, metaphors, all kinds of examples. It's like, it's an interesting challenge.
How many illustrations do you have in your book?
Not many, because actually illustrations are frowned upon in the publishing world.
Why?
Because there's an absolute correlation with the number of illustrations and the increase in the fewer people read the book.
So actually,
So if you're gonna do Das Kapital, who's gonna do the Communist Manifesto?
That metaphor flew past me.
Das Kapital, very thick economic text.
Oh, I see.
Communist Manifesto is what ignited the world.
I'm trying to do the Communist Manifesto. I don't want to say that.
Cut that from the tape.
That's not what he meant. He's not doing a communist manifesto.
You're now. Wait, you think, Kevin?
That's the title of the video. Viral.
Well, the trick is, there are some figures that help, but also just descriptions really help. Just walk people through verbal descriptions. Anyway, look, I think we have to do all this stuff. We have to show that that these ideas work in the machine learning world to get their attention. We have to show that we can do other things and bring people along. We have to sort of illustrate our theories. We have to join conversations. We have to go to conferences.
Yeah.
All that stuff. I don't think there's a shortcut to the communications problem. All right, that's enough yakking about that. I think we're done. I'm done.
Okay, you guys, thanks. I'm gonna.
Thank you.
You're getting turned off now.
Thank you.
Okay. Thank you guys for watching. Hold on, I gotta turn this meeting off. Okay. I think they're all talking to me, but I can't hear them anymore. So, thanks for watching. Hi, Falco. Hi, everybody. I think I might be streaming later on Twitch today. If you wanna join me there. If you're still watching this, you made it all the way through. Please like the video. I see there's 12 people watching right now. I'd love to see a bunch of likes. It helps the live streams get promoted. YouTube loves likes. So take care, you guys. I'll see you all later. Well, another Friday at least. We'll have another paper review on Friday. Goodbye. I'm trying to turn